Sklearn Ensemble. Description: explain in detail ensemble methods in scikit-learn. Sklearn combine multiple machine learning models to improve predictive performance, robustness, and generalization ability. Instead of relying on a single model, ensembles leverage the strengths of diverse models to make more accurate and reliable predictions. Inputs. Input 1. Explain in detail the input data. Typically a structured dataset containing features and corresponding target values. It can be a pandas data frame, NumPy array, or a similar data structure. Input 2. Explain in detail the type of ensemble method to be used, such as bagging, random forest, boosting, other boost, gradient boosting, or stacking. Outputs. Output 1. Explain in detail the predicted output for new, unseen data points. The output format depends on the task, like classification labels, regression values, or probabilities. Output 2. Explain in detail model parameters that represent the learned relationships between the input features and the target variable. These parameters are used to make predictions on new data. Steps. Step 1. Explain in detail model training. The ensemble method trains multiple base models on different subsets of the training data or using different model parameters. Step 2. Explain in detail prediction. The trained ensemble model combines the predictions from each individual base model to generate a final prediction. Metrics. Metric 1. Explain in detail accuracy. The percentage of correct predictions for classification tasks. Metric 2. Explain in detail mean squared error. MSE measures the average squared difference between predicted and actual values for regression tasks. Visualization plots. Visualization plot 1. Explain in detail feature importance. Plot visualizes the relative importance of different features in the prediction process. This can help identify the most influential features. Visualization plot 2. Explain in detail decision tree visualization for tree-based ensembles like random forest. You can visualize individual decision trees to understand how the model makes predictions. Fine-tune parameters. Parameter 1. Explain in detail nestimators. The number of base models trees, etc. in the ensemble. Increasing this can improve accuracy but may increase training time. Parameter 2. Explain in detail max depth. The maximum depth of individual trees in the ensemble. This helps prevent overfitting, which can occur when trees grow too deep. Uncertainty methods. Uncertainty method 1. Explain in detail confidence intervals. Measure the range of possible predictions, providing an estimate of how certain the model is about its predictions. Uncertainty method 2. Explain in detail ensemble variance. Calculate the variance across the predictions of the individual models within the ensemble. Higher variance indicates more uncertainty. Challenges and fixes. Challenge 1. Explain in detail overfitting. When the ensemble model is too complex and learns the training data too well, it may perform poorly on unseen data. Sample use case that resulted in challenge 1. A random forest model with a large number of trees and a very deep tree structure might overfit on a small dataset. Fixes to challenge 1. Reduce the number of trees nestimators. Limit the maximum depth of trees max depth. Or use techniques like cross-validation to monitor for overfitting during training. Challenge 2. Explain in detail high computational cost. Training ensemble models can be computationally expensive, especially with large datasets or complex base models. Sample use case that resulted in challenge 2. Training a gradient boosting model with many trees on a dataset with millions of rows and hundreds of features can be very time-consuming. Fixes to challenge 2. Use more efficient algorithms. Optimize hyperparameters like the learning rate in gradient boosting. Consider parallel processing, or explore cloud computing resources. sklearn Ensemble ADA Boost Regressor. Description: ADA Boost Regressor is a powerful ensemble learning algorithm for regression tasks. It combines multiple weak learners, typically decision trees, to create a strong learner that can achieve high accuracy. The algorithm works by assigning weights to each training instance. Instances that are misclassified by previous weak learners get higher weights, thus forcing subsequent learners to focus on them. This process iteratively improves the model's performance by focusing on difficult to classify instances. Inputs: XA2D array containing the features of the training data. Each row represents a data point, and each column represents a feature. YA1D array containing the target values for the training data. The target values must be numeric. Outputs: fitted model, the trained ADA Boost Regressor model. This model can be used to predict target values for new data points. Predictions: when the fitted model is applied to new data, it generates predictions for the target values. Steps: initialization: initialize the weights of all training instances equally. Iterative learning: for each iteration, fit a weak learner, typically a decision tree, to the training data. Calculate the error of the weak learner and update the weights of the training instances based on the error. Model aggregation: combine the predictions of all the weak learners using a weighted average, where the weights are determined by the performance of each weak learner. Metrics: mean absolute error measures the average absolute difference between the predicted and actual values. Root mean squared error RMSE measures the square root of the average squared difference between the predicted and actual values. R squared measures the proportion of variance in the target variable that is explained by the model. Visualization plots: feature importance plot shows the relative importance of each feature in the model. Residual plot plots the difference between the predicted and actual values. This can help identify patterns in the errors and reveal potential issues with the model. Fine-tune parameters: estimates the number of weak learners to use in the ensemble. Increasing this value generally improves accuracy but can also increase training time. Learning rate controls the contribution of each weak learner to the final prediction. Lower values reduce the influence of individual learners, making the model more robust to outliers. Uncertainty methods: bagging: training multiple ADA Boost Regressor models on different subsets of the training data. The predictions from these models can be averaged to estimate the uncertainty in the predictions. Bootstrap aggregating: bagging, a technique for reducing variance in predictions by creating multiple models on different subsamples of the data. This can be used to estimate the uncertainty of the model's predictions. Challenges and fixes. Challenge 1: overfitting. If the number of weak learners is too high or the learning rate is too large, the model can overfit the training data and perform poorly on new data. Sample use case: a model trained with 1000 estimators and a learning rate of 1.0 overfits the training data and generalizes poorly. Fixes: reduce the number of estimators, decrease the learning rate, use early stopping to prevent overfitting during training. Challenge 2: high variance. If the data is highly noisy or there are outliers, the model can have high variance, leading to unstable predictions. Sample use case: a model trained on noisy data exhibits large variations in predictions for similar data points. Fixes: use a smaller learning rate, regularize the weak learners, e.g., by using L1 or L2 regularization. Consider using a more robust base learner, e.g., a decision tree with a larger minimum leaf size. sklearn Ensemble Bagging Regressor. Description: Bagging regressor is an ensemble method that uses bootstrap aggregating bagging to create multiple decision trees and then averages their predictions. This helps to reduce variance and improve the accuracy of the model. It is particularly useful for dealing with complex datasets with high variance, where a single decision tree might overfit the data. Inputs. Base estimator. This is the base estimator used to create the individual decision trees. It can be any estimator that implements the fit and predict methods, such as decision tree regressor. Nestimators. This parameter controls the number of decision trees to create. A higher number of estimators generally leads to better performance but also increases computational cost. Max samples. This parameter controls the maximum number of samples to use when creating each decision tree. A value of 1.0 means that all samples are used, while a value less than 1.0 means that a random subset of samples is used. Max features. This parameter controls the maximum number of features to use when creating each decision tree. A value of 1.0 means that all features are used, while a value less than 1.0 means that a random subset of features is used. Bootstrap. This parameter controls whether to use bootstrap sampling when creating each decision tree. If set to true, each decision tree is trained on a random subset of the samples with replacement. Bootstrap features. This parameter controls whether to use bootstrap sampling for features when creating each decision tree. If set to true, each decision tree is trained on a random subset of the features with replacement. Outputs. Predictions. The model outputs predictions for the target variable. These predictions are based on the average predictions of the individual decision trees. Steps. Bootstrap sampling for each decision tree. A random subset of the training data is selected with replacement. Model training. Each decision tree is trained on its respective subset of data. Prediction aggregation. The predictions from all the individual decision trees are averaged to get the final prediction. Metrics. Mean squared error (MSE). This metric measures the average squared difference between the predicted and actual values. R-squared. This metric measures the proportion of the variance in the target variable that is explained by the model. Visualization plots. Feature importance plot. This plot shows the importance of each feature in the model. Residual plot. This plot shows the difference between the predicted and actual values. Fine-tune parameters. Nestimators. Increasing this value generally improves performance but also increases computational cost. Max samples. Decreasing this value can help to reduce overfitting but may also decrease performance. Max features. Decreasing this value can help to reduce overfitting but may also decrease performance. Uncertainty methods. Standard deviation of predictions. This method provides a measure of the uncertainty in predictions by calculating the standard deviation of the predictions from the individual decision trees. Challenges and fixes. Challenge 1. High variance in the predictions. Sample use case that resulted in challenge 1 when the model is trained on a small dataset or a dataset with a lot of noise. The predictions can have high variance. Fixes to challenge 1. Increase the number of estimators nestimators to reduce variance. Decrease the value of max samples or max features to reduce the variance of each individual tree. Challenge 2. Overfitting the data. Sample use case that resulted in challenge 2. When the model is trained on a large dataset with a lot of features, it can overfit the data and perform poorly on unseen data. Fixes to challenge 2. Use a smaller number of estimators nestimators to prevent overfitting. Increase the value of max samples or max features to reduce the variance of each individual tree. Use regularization techniques, such as L1 or L2 regularization, to prevent overfitting. sklearn Ensemble Extra Trees Classifier. Description: Extra Trees Classifier is an ensemble learning method for classification that operates by constructing a multitude of decision trees during training and outputting the class that is the mode of the class is classification or mean average prediction regression of the individual trees. Each decision tree is built on a random subset of the training data, bootstrap aggregating or bagging, and each tree is constructed with a random subset of features at each node. This randomness in both data and features ensures that the trees are correlated and diverse, which leads to a more robust and less prone to overfitting model. Inputs: X feature matrix of shape n samples. N features. Each row represents a data point and each column represents a feature. Y target variable of shape n samples. Contains the class labels for each data point in X. Outputs: predicted labels, the predicted class labels for new data points. Probability estimates the probability of each class for each data point in new data. Steps: bootstrap aggregating, bagging randomly sample with replacement from the training data to create multiple subsets. Each subset will be used to train a separate decision tree. Random subspace for each tree and at each node. Randomly select a subset of features to be considered for splitting the node. Decision tree construction: build a decision tree for each subset of data and features. Prediction for new data. Each tree makes a prediction. The final prediction is the average of the predictions of all trees for regression or the class. That is the mode of the predictions of all trees for classification. Metrics: accuracy, the proportion of correctly classified data points. Precision, the proportion of correctly predicted positive cases out of all predicted positive cases. Recall, the proportion of correctly predicted positive cases out of all actual positive cases. F1 score, the harmonic mean of precision and recall. Visualization plots. Decision tree plots visualize the structure of each individual decision tree. Feature importance plots show the importance of each feature in the classification process. Fine-tune parameters. Nestimators, the number of trees in the forest. Increasing the number of trees generally improves performance but can also increase computational time. Max depth, the maximum depth of each tree. This parameter helps to control overfitting and can improve generalization performance. Max features, the number of features to consider when looking for the best split at each node. Uncertainty methods. Out-of-bag OOB error uses the trees that were not trained on a specific data point to estimate the uncertainty for that point. Confidence intervals can be calculated for the predicted probabilities, providing a measure of uncertainty about the prediction. Challenges and fixes. High computational cost. Training a large number of trees can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 1: training an extra trees classifier with 1000 trees on a dataset with millions of samples and thousands of features. Fixes to challenge 1: reduce the number of trees. Start with a smaller number of trees and gradually increase it until the performance plateaus. Use parallelization. Leverage multi-core CPUs or GPUs to speed up the training process. Optimize hyperparameters. Experiment with different hyperparameter values to find the best balance between performance and computational cost. Overfitting. If the trees are too deep or the number of features is too high, the model may overfit to the training data. Sample use case that resulted in Challenge 2: training an extra trees classifier on a dataset with a high number of features and a limited number of samples. Fixes to Challenge 2: use a smaller number of features. Use feature selection techniques to reduce the dimensionality of the data. Reduce the depth of the trees. Limit the maximum depth of the trees to prevent overfitting. Use regularization techniques. Techniques like L1 or L2 regularization can help to prevent overfitting. Interpretability. It can be difficult to interpret the predictions of an extra trees classifier because it is an ensemble model composed of many individual trees. Sample use case that resulted in Challenge 3: understanding the reasons behind the classification. Decision made by an extra trees classifier. Fixes to Challenge 3: use feature importance plots to identify the most important features. Use partial dependence plots to visualize how individual features influence the predictions. Use decision tree visualization tools to understand the structure of individual trees. sklearn Ensemble Extra Trees Classifier. Description: Extra Trees Classifier is a powerful ensemble learning method that leverages multiple decision trees to make predictions. It builds upon the random forest algorithm, introducing additional randomness in the feature selection process during the tree construction. This randomness allows extra trees classifier to be more robust to overfitting and less susceptible to noise in the data. Inputs: X a 2D array-like structure representing the input features, where each row corresponds to a sample and each column represents a feature. Y a 1D array-like structure representing the target values for each sample. Outputs: predictions: an array containing the predicted class labels for new data points. Probabilities: a 2D array containing the probabilities of each sample belonging to each class. Steps: bootstrap aggregating, bagging randomly sample with replacement from the training data to create multiple subsets. Random subspace: randomly select a subset of features for each tree in the ensemble. Decision tree construction: build a decision tree on each subset using the selected features, with the goal of minimizing impurity at each node. Prediction: combine the predictions from all individual trees using a majority vote for classification or averaging for regression. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly predicted positive samples out of all samples predicted as positive. Recall: the proportion of correctly predicted positive samples out of all actual positive samples. F1 score: a harmonic mean of precision and recall. AUC area under the curve: a measure of the classifier's ability to distinguish between classes. Visualization plots: feature importance plot visualizes the relative importance of each feature in the decision-making process. Decision tree visualization plots the structure of individual decision trees in the ensemble. ROC curve plots the true positive rate against the false positive rate for different thresholds. Fine-tune parameters: nestimators: the number of trees in the ensemble. Max depth: the maximum depth of each individual tree. Minsamples: split: the minimum number of samples required to split an internal node. Minsamples leaf: the minimum number of samples required to be at a leaf node. Max features: the number of features to consider when looking for the best split. Uncertainty methods: Bagging the variance in predictions across multiple trees can be used as a measure of uncertainty. Out-of-bag OOB error. The error on samples not used in the training of a given tree provides an estimate of the model's generalization error. Confidence scores for classification problems. The probability assigned to each class can be interpreted as a measure of confidence. Challenges and fixes. Challenge 1: overfitting. If the number of trees or the depth of the trees is too large, the model may overfit the training data and perform poorly on unseen data. Sample use case that resulted in challenge 1: using a very large number of trees with a high max depth on a small dataset. Fixes to challenge 1: reduce the number of trees in estimators or the maximum depth max depth. Use regularization techniques like pruning or early stopping to prevent overfitting. Use cross-validation to evaluate the model's performance on unseen data and tune parameters accordingly. Challenge 2: high variance due to the random nature of feature selection. The predictions of individual trees can vary significantly, leading to high variance in the ensemble's predictions. Sample use case that resulted in challenge 2: using a very small number of features max features or a small number of trees in estimators. Fixes to challenge 2: increase the number of trees in estimators to reduce the impact of individual tree variance. Increase the number of features max features to improve the diversity of the trees in the ensemble. Use bootstrap aggregating bagging to create multiple subsets of the training data and train trees on each subset, further reducing variance. sklearn Ensemble Extra Trees Regressor. Description: Extra Trees Regressor is an ensemble learning method for regression that operates by constructing a multitude of decision trees during training and outputting the mean average prediction of the individual trees. Each tree is built using a random subset of features and data points, leading to a diverse ensemble. This randomness helps in preventing overfitting, making Extra Trees Regressor robust to noisy data. Inputs. X. This is the input feature matrix, where each row represents a data point and each column represents a feature. The values in X can be numerical or categorical. Y. This is the target variable that the model aims to predict. It is a one-dimensional array containing the values for each data point in X. Outputs. Predictions. The model outputs a prediction for each data point in the input feature matrix X. These predictions represent the estimated values of the target variable based on the trained model. Steps. Tree construction. The model constructs multiple decision trees, each using a random subset of features and data points from the training set. This randomness ensures diversity in the ensemble. Prediction averaging. During prediction, each tree in the ensemble makes a prediction for the given data point. The final prediction is the average of the predictions made by all the individual trees. Metrics. Mean squared error (MSE) measures the average squared difference between the predicted and actual values. It's a common metric for regression tasks, emphasizing larger errors. R-squared represents the proportion of the variance in the target variable that is explained by the model. A higher R-squared value indicates a better fit. Visualization plots. Feature importance plot displays the importance of each feature in the model's predictions. This plot helps identify the most influential features. Partial dependence plots visualizes the relationship between a specific feature and the predicted outcome, while holding other features constant. It helps understand how changes in a feature influence predictions. Fine-tune parameters. Nestimators controls the number of trees in the ensemble. Increasing this value often improves performance, but can increase computation time. Max depth limits the maximum depth of individual trees, preventing overfitting. Deeper trees can capture complex relationships but risk overfitting. Min-sample split, minimum number of data points required to split a node in a tree. A higher value prevents overfitting to small groups of data points. Max features controls the number of features randomly selected at each node split. It helps in diversifying the trees and reducing variance. Uncertainty methods. Bagging by randomly sampling data points and features for each tree. The model implicitly captures uncertainty. The variance in predictions across the ensemble provides an indication of uncertainty. Confidence intervals depending on the implementation. Confidence intervals for predictions can be calculated, quantifying the range of possible values with a certain degree of confidence. Challenges and fixes. Challenge 1: overfitting occurs when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1: using a large number of trees estimators and a high maximum depth. Max depth without sufficient data can lead to overfitting. Fixes to challenge 1: reduce the number of trees estimators. Limit the maximum depth of individual trees. Max depth. Increase the minimum number of samples required to split a node. Min-sample split. Consider using techniques like cross-validation to evaluate model performance and prevent overfitting. Challenge 2: high computational cost. Building a large number of trees can be computationally expensive, especially with large datasets. Sample use case that resulted in challenge 2: training a model with a high number of trees estimators and a large dataset can take significant time. Fixes to challenge 2: reduce the number of trees estimators. Consider using parallel processing techniques to speed up training. Optimize the hyperparameters to reduce the number of splits and nodes in the trees. Explore alternative algorithms like random forest, which may have a faster training time for similar performance. sklearn Ensemble Gradient Boosting Classifier. Description: Gradient boosting classifier is an ensemble method in scikit-learn that combines multiple decision trees to create a strong predictive model. It works by sequentially adding trees, each focusing on correcting the errors made by the previous trees. This iterative process gradually improves the model's accuracy. Inputs: X feature matrix containing the independent variables. Each row represents a sample, and each column represents a feature. Y target vector containing the dependent variable. This vector should be of the same length as the number of rows in the feature matrix. Outputs: model a trained gradient boosting classifier object. This object can be used to predict class labels for new data. Predictions: the predicted class labels for the input data. Steps: initialization: the first tree is trained on the entire dataset. Iterative training: in each iteration, a new decision tree is trained to predict the residuals errors of the previous model. Weighted aggregation: the predictions of all the individual trees are weighted and combined to produce the final prediction. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of true positives among all predicted positives. Recall: the proportion of true positives among all actual positives. F1 score: a harmonic mean of precision and recall. AUC: area under the curve, the area under the receiver operating characteristic ROC curve, which measures the model's ability to distinguish between different classes. Visualization plots: feature importance plot visualizes the relative importance of each feature in the model. Decision tree plots visualizes the structure of individual decision trees in the ensemble. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve plots precision against recall for different classification thresholds. Fine-tune parameters. Estimates the number of decision trees in the ensemble. Increasing this value can improve accuracy but may increase training time. Learning rate the contribution of each tree to the final prediction. Smaller values can lead to smoother decision boundaries but may require more trees for convergence. Max depth the maximum depth of each decision tree. Smaller values can prevent overfitting but may reduce accuracy. Min-samples split the minimum number of samples required to split a node. Larger values can prevent overfitting but may reduce accuracy. Min-samples leave the minimum number of samples required to be at a leaf node. Larger values can prevent overfitting but may reduce accuracy. Subsample the fraction of samples used for training each tree. Values less than 1 can reduce overfitting and improve generalization. Uncertainty methods. Confidence intervals calculate confidence intervals for the predicted probabilities. Out-of-bag predictions use the predictions from trees that were not used to train a specific sample to estimate uncertainty. Challenges and fixes. Challenge 1 overfitting. Sample use case that resulted in challenge 1 when the model is trained on a small dataset or with a large number of features. It may learn the training data too well and fail to generalize to unseen data. Fixes to challenge 1. Reduce the number of features. Use regularization techniques, such as L1 or L2 regularization. Use early stopping to prevent the model from overfitting the training data. Increase the minimum number of samples required to split a node. Min-samples split and the minimum number of samples required to be at a leaf node. Min-samples leaf. Challenge 2 high training time. Sample use case that resulted in challenge 2 when the dataset is very large or the number of trees in the ensemble is high. Training the model can take a significant amount of time. Fixes to challenge 2. Reduce the number of trees in the ensemble. Estimators. Use a smaller learning rate. Use a smaller maximum depth for the tree's max depth. Use a smaller subsample fraction. Use a parallel processing library, such as Dask or Joblib, to speed up training. Use a GPU for training, if available. Challenge 3 interpretability. Sample use case that resulted in challenge 3 gradient boosting classifier can be difficult to interpret due to the complex nature of the ensemble. Fixes to challenge 3. Use feature importance plots to identify the most important features. Use partial dependence plots to visualize the relationship between a specific feature and the predicted outcome. Use SHAP's happily additive explanations to explain the contribution of each feature to the prediction for a specific sample. sklearn Ensemble Gradient Boosting Regressor. Description Gradient Boosting Regressor is a powerful ensemble learning method that combines multiple decision trees to make predictions. It works by sequentially adding trees, each one trying to correct the errors made by the previous trees. This iterative process leads to improved accuracy and robustness compared to individual trees. Inputs. X. The training data, represented as a 2D array of features. Each row corresponds to a sample, and each column represents a feature. Y. The target variable, represented as a 1D array of values. Outputs. Predictions. The predicted values for new input data. Model a trained gradient boosting regressor object that can be used to make predictions. Steps. Initialization. A simple model, like a constant value, is used to make initial predictions. Iterative tree building. Calculate the residuals errors between the current model's predictions and the true values. Train a decision tree on these residuals. Add the predictions from this tree to the current model's predictions, with a weight proportional to its importance. Repeat step 2 until a stopping criterion is met, e.g., maximum number of trees, minimum improvement in error. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual values. R squared R2, a statistical measure that represents the proportion of the variance in the target variable that is explained by the model. Visualization plots. Feature importance plot shows the relative importance of each feature in the model. Partial dependence plots PDP visualize the relationship between a feature and the target variable, while keeping other features constant. Fine-tune parameters. Nestimators the number of trees in the ensemble. Increasing this generally leads to better performance, but may increase training time. Learning rate controls the contribution of each tree to the final prediction. Smaller values result in slower learning but may lead to better generalization. Max depth. The maximum depth of each decision tree. Deeper trees can learn more complex patterns but are prone to overfitting. Minsamples split. The minimum number of samples required to split an internal node. Uncertainty methods. Prediction intervals can be obtained by using techniques like bootstrapping or quantile regression. These intervals provide a range of plausible values for the prediction, reflecting the model's uncertainty. Challenges and fixes. Challenge 1. Overfitting. If the model is too complex, it might learn the training data too well and fail to generalize to new data. Sample use case. A model with high depth and a large number of trees might overfit a dataset with noisy features. Fixes. Reduce the model's complexity by decreasing the maximum depth, using regularization techniques, or early stopping. Challenge 2. Slow training time. Gradient boosting can be computationally expensive, especially for large datasets. Sample use case. Training a model with a large number of trees and features on a large dataset might take a significant amount of time. Fixes. Use techniques like subsampling to reduce the size of the data used for each tree. Utilize parallel processing to speed up the training process. Consider using lighter weight models like random forest or decision tree if training time is a major concern. sklearn Ensemble Isolation Forest. Description. Explain in detail. Isolation forest is an unsupervised anomaly detection algorithm in scikit-learn that leverages the concept of random forests to identify outliers. It works by randomly partitioning the data space and constructing a forest of decision trees. The algorithm identifies outliers as instances that are easily isolated, meaning they are far away from other data points and can be separated with fewer splits in pay. Decision tree. Inputs. Input 1. Explain in detail. The input data is a NumPy array or pandas data frame containing pay features to be analyzed. Each row represents a data point, and each column represents a feature. Input 2. Explain in detail. The contamination parameter is used to estimate the percentage of outliers in the dataset. It represents the expected proportion of outliers in the input data. This parameter is optional, and if not specified, the algorithm will automatically estimate the contamination level based on the data. Outputs. Output 1. Explain in detail. The isolation forest model returns anomaly scores for each data point. These scores indicate how likely a data point is to be an outlier. Lower scores represent a higher likelihood of being an outlier. Output to explain in detail the isolation forest model also provides a decision function that returns a score for each data point. This score reflects the distance of a data point from the decision boundary. Positive values indicate an outlier, while negative values indicate a typical data point. Steps. Step 1. Explain in detail the isolation forest algorithm begins by randomly selecting a feature and a random split value within the range of that feature. This process is repeated for each data point, creating a decision tree. Step 2. Explain in detail. This process of random partitioning is repeated multiple times, creating an ensemble of decision trees, which forms the forest. Metrics. Metric 1. Explain in detail. The isolation forest algorithm does not directly use specific metrics, like accuracy or precision. Instead, it focuses on providing anomaly scores that indicate the likelihood of an instance being an outlier. Metric 2. Explain in detail. The algorithm can be evaluated based on the distribution of anomaly scores. For example, a good model would show a clear separation between the scores of normal data points and outlier data points. Visualization plots. Visualization plot 1. Explain in detail. Scatter plots can be used to visualize the data points and their anomaly scores. This can help to identify clusters of outliers. Visualization plot 2. Explain in detail. Histograms can be used to visualize the distribution of anomaly scores. This can help to understand the range of scores and identify potential thresholds for outlier detection. Fine-tune parameters. Parameter 1. Explain in detail. The contamination parameter controls the expected proportion of outliers in the data. This parameter can be adjusted to optimize the detection of outliers. Parameter 2. Explain in detail. The number of estimators parameter controls the number of decision trees in the forest. Increasing this parameter can improve the robustness of the model. Uncertainty methods. Uncertainty method 1. Explain in detail. The isolation forest algorithm does not explicitly provide uncertainty estimates. It focuses on providing anomaly scores that indicate the likelihood of an instance being an outlier. Uncertainty method 2. Explain in detail. To assess the uncertainty of the model, you can analyze the variability in anomaly scores across different runs of the algorithm with different random seeds. Challenges and fixes. Challenge 1. Explain in detail. High dimensionality in the data can lead to challenges for the isolation forest algorithm, as it relies on random partitioning of the feature space. High dimensionality can make it difficult to effectively isolate outliers. Sample use case that resulted in challenge 1. A dataset with hundreds of features can lead to high dimensionality and impact the performance of isolation forest. Fixes to challenge 1. Feature selection techniques can be used to reduce the dimensionality of the data before applying isolation forest. This can improve the accuracy and efficiency of outlier detection. Another approach is to use dimensionality reduction techniques such as PCA or T-SNE. Challenge 2. Explain in detail. The isolation forest algorithm can be sensitive to the presence of highly correlated features. These features can lead to an overestimation of the isolation of data points and result in false positives. Sample use case that resulted in challenge 2. A dataset with multiple features measuring similar aspects of a system can lead to highly correlated features. Fixes to challenge 2. Feature engineering techniques can be used to remove or transform highly correlated features. This can improve the performance of the algorithm by reducing the influence of these features on the outlier detection process. Alternatively, using methods like random forest with feature permutation can help in detecting correlated features and adjusting for them. sklearn Ensemble Random Forest Classifier. Description: the random forest classifier is an ensemble learning method for classification tasks that operates by constructing a multitude of decision trees during training and outputting the class. That is, the mode of the class is classification or mean average prediction regression of pay. Individual trees. Inputs. X the training input samples. This should be a 2D array, where each row represents a sample and each column represents a feature. Y the target output values. This should be a 1D array, where each element represents the class label of the corresponding input sample. Outputs. The trained random forest classifier model. The predicted class labels for new input samples. Steps. 1. Bootstrap aggregating. Bagging. The random forest classifier uses bootstrap aggregating, which involves creating multiple subsets of the training data by sampling with replacement. Each subset is called a bootstrap sample. 2. Decision tree construction. For each bootstrap sample, a decision tree is constructed. However, instead of considering all features at each split node, the algorithm randomly selects a subset of features, usually the square root of the total number of features for classification. 3. Prediction. To make predictions for new input samples, the random forest classifier combines the predictions of all individual decision trees. In classification, the most common class label predicted by the trees is chosen as the final prediction. In regression, the average prediction of the trees is taken as the final prediction. Metrics. Accuracy. The percentage of correctly classified samples. Precision. The ratio of correctly predicted positive samples to the total number of predicted positive samples. Recall. The ratio of correctly predicted positive samples to the total number of actual positive samples. F1 score. The harmonic mean of precision and recall. AUC area under the curve. A measure of the model's ability to distinguish between positive and negative samples. Visualization plots. Feature importance plot. This plot shows the importance of each feature in the model. Decision tree visualization. Visualizing individual decision trees within the forest provides insight into the decision process. Confusion matrix. This matrix displays the number of true positives, true negatives, false positives, and false negatives. Fine-tune parameters. Nestimators. The number of decision trees in the forest. Increasing this number typically improves model performance but also increases training time. Max depth. The maximum depth of each decision tree. Limiting this depth can help prevent overfitting. Minsamples split. The minimum number of samples required to split an internal node. Minsamples leaf. The minimum number of samples required to be at a leaf node. Max features. The number of features to consider when looking for the best split at each node. Bootstrap. Whether to use bootstrap aggregating when creating the bootstrap samples. Criterion. The function to measure the quality of a split. Uncertainty methods. Out of bag OOB score. This score is calculated using the samples that were not included in pay. Bootstrap sample for each tree. It provides an estimate of the model's generalization performance. Confidence intervals. Confidence intervals can be calculated for the predicted class probabilities. Challenges and fixes. Challenge 1. Overfitting. Random forests can overfit the training data if the number of trees is too large or if the trees are allowed to grow too deep. Sample use case. A model trained on a small dataset with a large number of trees in a deep max depth might overfit and perform poorly on unseen data. Fixes. Reduce the number of trees. Nestimators experiment with decreasing the number of trees to prevent the model from becoming too complex. Limit the maximum depth of the trees. Max depth. Setting a reasonable maximum depth helps to Prevent individual trees from becoming too specific to the training data. Use early stopping. Monitor the performance of the model on a validation set during training and stop training when performance on the validation set starts to decline. Challenge. Too high variance random forests can be sensitive to the specific training data, leading to high variance in the predictions. Sample use case. A model trained on a dataset with a few outliers might be heavily influenced by those outliers, leading to inaccurate predictions for new samples. Fixes. Increase the number of trees. Estimators. A larger number of trees can help to reduce the impact of individual outliers. Increase the minimum number of samples required to split a node. Min samples split. This helps to prevent the trees from becoming too sensitive to individual data points. Use bagging. Bootstrap aggregating can help to reduce variance by averaging the predictions of multiple trees trained on different subsets of the data. Challenge 3. Interpretability. Random forests are often considered black boxes because they are difficult to interpret. Sample use case. Understanding why a specific prediction was made can be challenging due to the complexity of the ensemble of decision trees. Fixes. Feature importance analysis. Examining the feature importance scores can provide insights into which features are most influential in the model's predictions. Partial dependence plots. These plots can visualize the relationship between a specific feature and the model's output. Sharp values. These values provide an explanation of how each feature contributes to the prediction for a given instance. sklearn Ensemble Random Forest Regressor. Description. Explain in detail. The random forest regressor is an ensemble learning method for regression that operates by constructing a multitude of decision trees during training and outputting the mean average prediction of the individual trees. Each tree is built on a random subset of the features and training samples. This process helps to mitigate overfitting and enhance the model's generalization ability. Inputs. Input 1. Explain in detail X. This input represents the feature matrix of the dataset. Each row corresponds to a data point, and each column corresponds to a feature. Input 2. Explain in detail why this input represents the target variable, containing the values that the model aims to predict. Outputs. Output 1. Explain in detail. The random forest regressor produces a prediction for each input data point. The output is a numerical value representing the model's estimated value for the target variable. Output 2. Explain in detail. The random forest regressor also provides attributes that offer insights into the model's structure and performance. These attributes include feature importances. A list of feature importance scores indicating the relative contribution of each feature to the model's predictions. OOB score. The out-of-bag OOB score, which is an estimate of the model's prediction accuracy on unseen data, calculated using the samples not used in building each tree. Steps. Step 1. Explain in detail. The algorithm randomly selects a subset of features and data points from the training set. Step 2. Explain in detail. A decision tree is constructed using the chosen data and features. Step 3. Explain in detail. This process of random feature and sample selection is repeated multiple times, resulting in a forest of decision trees. Step 4. Explain in detail. During prediction, the model averages the predictions of all the individual trees in the forest. Metrics. Metric 1. Explain in detail. Mean squared error (MSE), a common metric used to evaluate regression models. It measures the average squared difference between the predicted and actual values. Metric 2. Explain in detail. R squared R2 represents the proportion of the variance in a dependent variable that is predictable from the independent variables. A higher R-squared value indicates a better fit. Visualization plots. Visualization plot 1 explain in detail feature importance plot displays the importance scores of each feature, providing insights into which features have the most significant influence on the models. Predictions. Visualization plot 2 explain in detail partial dependence plots visualize the relationship between a single feature and the target variable, while holding other features constant. They help understand the impact of individual features on the model's predictions. Fine-tune parameters. Parameter 1 explain in detail nestimators determines the number of trees in the forest increasing. This value generally improves performance but can also increase training time. Parameter 2 explain in detail max depth controls the maximum depth of each decision tree. Limiting depth can help prevent overfitting by restricting the complexity of the trees. Parameter 3 explain in detail min samples split specifies the minimum number of samples required to split an internal node. A higher value promotes simpler trees and can help prevent overfitting. Parameter 4 explain in detail max features controls the number of features randomly selected at each split. Setting this value lower can lead to less correlated trees. Parameter 5 explain in detail bootstrap indicates whether to use bootstrap aggregation, where samples are randomly drawn with replacement. This technique is often used to reduce variance and improve generalization. Uncertainty methods. Uncertainty method 1 explain in detail out-of-bag OOB prediction provides an estimate of pay. Models prediction uncertainty by averaging the predictions of trees that were not trained on pay specific data point being predicted. Uncertainty method 2 explain in detail confidence intervals for each prediction. A confidence interval can be constructed based on the distribution of predictions from pay individual trees. The width of the confidence interval reflects the uncertainty associated with the prediction. Challenges and fixes. Challenge 1 explain in detail high training time constructing a large number of trees can be computationally expensive, leading to long training times. Sample use case that resulted in challenge 1 training a random forest model on a data set with a million data points and hundreds of features might take several hours. Fixes to challenge 1. Reduce the number of trees nestimators. Employ parallelization techniques to train trees simultaneously. Utilize a GPU for accelerated training. Challenge 2 explain in detail overfitting if the model is too complex deep trees. High number of trees. It can overfit the training data and perform poorly on unseen data. Sample use case that resulted in challenge 2 a model with a large number of trees and high depth might perfectly predict the training data but fail to generalize to new examples. Fixes to challenge 2. Limit the maximum depth of the tree's max depth. Increase the minimum samples required for splitting the node min samples split. Adjust the number of features considered at each split max features. Challenge 3 explain in detail high memory consumption storing a large number of trees in memory can consume significant resources. Sample use case that resulted in challenge 3 training a random forest model with a million trees on a dataset with a large number of features could exhaust available memory. Fixes to challenge 3. Reduce the number of trees nestimators. Employ techniques like out-of-call learning to process data in batches. Consider using a distributed computing environment. sklearn Ensemble Random Trees Embedding. Description explain in detail random trees embedding is a dimensionality reduction technique that uses an ensemble of decision trees to learn a low-dimensional embedding of the input data. It works by constructing multiple decision trees. where each tree is trained on a random subset of the features and samples. The output of the random tree's embedding is a sparse matrix where each row represents a data point, and each column represents a leaf node in one of the trees. The value in each cell represents the number of times the corresponding data point has fallen into that leaf node across all trees. This sparse matrix can then be used as input to other machine learning models, such as clustering or classification algorithms. Inputs. Input 1. Explain in detail X. This is the input data, which should be a 2D array of shape n samples. N features. Input 2. Explain in detail Y. This is the target variable, which is only used if the sparse output parameter is set to false. It should be a 1D array of shape n samples. Outputs. Output 1. Explain in detail X transformed. This is the transformed data, which is a sparse matrix of shape n samples. N outputs, where n outputs is the number of leaf nodes in the ensemble of trees. Output 2. Explain in detail Y. This is the target variable, which is only returned if the sparse output parameter is set to false. It is the same as the input Y. Steps. Step 1. Explain in detail the random trees embedding algorithm first constructs an ensemble of decision trees. Each tree is trained on a random subset of the features and samples. Step 2. Explain in detail for each data point in the input data. The algorithm determines the leaf node that it falls into for each tree in the ensemble. The output is a sparse matrix where each row represents a data point and each column represents a leaf node in one of the trees. The value in each cell represents the number of times the corresponding data point has fallen into that leaf node across all trees. Metrics. Metric 1. Explain in detail. There are no specific metrics for evaluating the performance of random trees embedding, as it is a dimensionality reduction technique rather than a predictive model. However, the quality of the embedding can be assessed by examining the distribution of the transformed data, and by evaluating the performance of other machine learning models that are trained on the transformed data. Metric 2. Explain in detail. No applicable metrics. Visualization plots. Visualization plot 1. Explain in detail. A scatter plot of the transformed data can be used to visualize the embedding. This can help to identify any clusters or patterns in the data. Visualization plot 2. Explain in detail. No applicable plots. Fine-tune parameters. Parameter 1. Explain in detail. Nestimators. This parameter specifies the number of trees in the ensemble. A higher value generally results in a more robust embedding, but can also increase the training time. Parameter 2. Explain in detail. Max depth. This parameter specifies the maximum depth of each tree in the ensemble. A higher value can lead to overfitting, while a lower value may result in an underfitting model. Parameter 3. Explain in detail. Min samples split. This parameter specifies the minimum number of samples required to split an internal node. A higher value can prevent overfitting, while a lower value may result in an underfitting model. Parameter 4. Explain in detail. Sparse output. This parameter determines whether the output is a sparse matrix or a dense array. If set to true, the output will be a sparse matrix, which can be more efficient for storing and processing large datasets. If set to false, the output will be a dense array. Uncertainty methods. Uncertainty method 1. Explain in detail. No applicable uncertainty methods. Uncertainty method 2. Explain in detail. No applicable uncertainty methods. Challenges and fixes. Challenge 1. Explain in detail overfitting. If the number of trees or the maximum depth of the trees is too large, the model can overfit the training data and may not generalize well to new data. Sample use case that resulted in challenge 1. A random trees embedding model with a large number of trees and a high maximum depth was trained on a dataset with a small number of samples. The model overfitted the training data and performed poorly on the test data. Fixes to challenge 1. Use cross-validation to select the optimal number of trees and the maximum depth of the trees. This can help to prevent overfitting. Challenge 2. Explain in detail underfitting if the number of trees or the maximum depth of trees is too small. The model may not be able to capture the underlying structure of the data. Sample use case that resulted in challenge 2. A random trees embedding model with a small number of trees and a low maximum depth was trained on a dataset with a complex structure. The model underfitted the data and did not perform well on the test data. Fixes to challenge 2. Increase the number of trees or the maximum depth of the trees. This can help to improve the performance of the model. Challenge 3. Explain in detail computational cost. Random trees embedding can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 3. A random trees embedding model was trained on a large dataset with a high number of features. The training process took a long time. Fixes to challenge 3. Use a smaller number of trees or a lower maximum depth to reduce the computational cost. Alternatively, you can try using a different dimensionality reduction technique, such as PCA, which is generally faster. sklearn Ensemble Stacking Classifier. Description. The stacking classifier is a powerful ensemble method in scikit-learn that combines multiple Bayes estimators classifiers to create a more robust and accurate prediction model. It works by training individual Bayes models on the original dataset and then training a final meta estimator on the predictions from the Bayes models. This process leverages the strengths of different models and helps to mitigate weaknesses, leading to improved generalization performance. Inputs. Bayes estimators list a list of Bayes classifiers that will be trained on the original dataset. Each Bayes estimator should be an instance of a scikit-learn classifier class, e.g. logistic regression, random forest classifier, gradient boosting classifier, etc. Final estimator, a scikit-learn classifier that will be trained on the predictions of the Bayes estimators. This meta estimator combines the outputs of the Bayes models to make the final prediction. Outputs. Predictions. The predicted class labels for new data points. Probability is optional if the final estimator supports probability estimation. It will also return the probability of each class for each data point. Steps. Training. Each Bayes estimator is trained independently on the original dataset. The predictions made by each Bayes estimator are collected. Meta estimator training. The final estimator is trained using the predictions from the Bayes estimators as features. Metrics. Accuracy measures the proportion of correctly classified instances. Precision measures the proportion of true positives among all positive predictions. Recall measures the proportion of true positives among all actual positive instances. F1 score the harmonic mean of precision and recall. Visualization plots. Feature importance plots the relative importance of each Bayes estimator's predictions in the final model. Confusion matrix visualizes the classification performance, showing the number of true positives, false positives, true negatives, and false negatives. Fine-tune parameters. Bayes estimators experiment with different Bayes classifiers and their hyperparameters to find the best combination. Final estimator. Choose a final estimator that is suitable for the specific task and adjust its Hyperparameters accordingly. Stacking parameters adjust the CV cross-validation folds and pass-through parameters to control the stacking process. Uncertainty methods. Confidence scores use the probability estimates provided by the final estimator to assess the uncertainty of predictions. Ensemble variance calculate the variance of predictions across the base estimators to estimate uncertainty. Challenges and fixes. Challenge 1: overfitting to base estimator predictions. Sample use case: a stacking model might overfit to the predictions of a single strong base estimator, leading to poor generalization on unseen data. Fixes. Use cross-validation during meta-estimator training to prevent overfitting. Regularize the final estimator to reduce its complexity. Experiment with different base estimators and their hyperparameters. Challenge 2: high computational cost. Sample use case stacking can be computationally expensive, especially with a large number of base estimators or a large dataset. Fixes. Reduce the number of base estimators or simplify their models. Use efficient algorithms for meta-estimator training. Optimize code for parallel processing or distributed computing. sklearn Ensemble Stacking Regressor. Description. The stacking regressor in scikit-learn is an ensemble learning method that combines multiple base regression models to create a more powerful and robust model. It works by training a meta-regressor on the predictions of the base models. The meta-regressor learns how to best combine the predictions of the base models to improve the overall prediction accuracy. Inputs. Estimators: a list of base regression models to be combined. Each element in the list should be a scikit-learn estimator object, e.g. linear regression, random forest regressor, gradient boosting regressor. Final estimator: a meta-regressor that learns to combine the predictions of the base models. This can be any scikit-learn regression estimator. Outputs. Predictions: the predicted values for the target variable, based on the combined predictions of the base models. Steps. Stage 1: the base models are trained on the input data. Stage 2: the predictions of the base models are used as input to train the meta-regressor. Stage 3: the trained meta-regressor is used to make predictions on new data. Combining the predictions of the base models. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual values. Root mean squared error RMSE the square root of the MSE. Providing a measure of the prediction error in the same units as the target variable. R squared a measure of the model's goodness of fit, indicating the proportion of variance in the target variable that is explained by the model. Mean absolute error may measures the average absolute difference between the predicted and actual values. Visualization plots. Residual plots visualize the difference between the predicted and actual values to identify patterns or outliers. Feature importance plots visualize the importance of each feature in the model's predictions. Learning curves plot the model's performance on training and validation data to assess model complexity and identify overfitting or underfitting. Fine-tune parameters. Estimators experiment with different combinations of base models to find the optimal combination for your specific problem. Final estimator: choose a meta-regressor that is suitable for the type of data and task. CV: the number of folds to use in cross-validation when training the base models and the meta-regressor. N jobs: the number of CPU cores to use for parallel processing. Uncertainty methods. Confidence intervals provide a range of values within which the true prediction is likely to fall. Prediction intervals provide a range of values within which the true prediction is likely to fall. taking into account the uncertainty in the model's parameters. Challenges and fixes. Challenge 1: overfitting when the model is too complex and learns the training data too well. It may not generalize well to new data. Sample use case that resulted in challenge 1: training a stacking regressor with a large number of base models on a small dataset, leading to a high variance model. Fixes to challenge 1. Use regularization techniques, e.g., L1 or L2 regularization to reduce the complexity of the models. Use cross-validation to select the optimal model complexity and avoid overfitting. Employ early stopping to prevent the model from training for too long and overfitting the data. Challenge 2: high computational cost. Stacking regressor can be computationally expensive, especially when using many base models or a large dataset. Sample use case that resulted in challenge 2: training a stacking regressor with multiple complex base models on a large dataset, leading to long training times. Fixes to challenge 2. Use less complex base models to reduce the computational cost. Use parallel processing to speed up training. Consider using a subset of the data for training if computational resources are limited. Challenge 3: data leakage. If the meta-regressor has access to information that was used to train the base models, it can lead to data leakage and over-optimistic performance estimates. Sample use case that resulted in challenge 3: using the same data to train both the base models and the meta-regressor, resulting in the meta-regressor being able to cheat and learn patterns from the training data. Fixes to challenge 3. Use cross-validation techniques that ensure that the meta-regressor is trained on data that is not used to train the base models. Use a holdout set of data to evaluate the model's performance without data leakage. sklearn Ensemble voting classifier. Description. The voting classifier is a scikit-learn ensemble method that combines the predictions of multiple individual classifiers estimators to produce a final prediction. It works by averaging or voting on the predictions of each individual classifier, thereby harnessing the strengths of multiple models and potentially achieving better performance than any single model alone. Inputs. Estimators: a list of tuples of estimator name. Estimator instance. The estimator name is a string used to identify the estimator in the ensemble. And the estimator instance is a fitted scikit-learn estimator object. Voting: a string, either hard or soft. Specifying the voting strategy. Hard voting uses the predicted class labels from each estimator, while soft voting uses the predicted probabilities of each class from each estimator. Outputs. Predictions: a NumPy array of predicted class labels or probabilities, depending on the voting strategy. Fitted ensemble: the fitted voting classifier object, which can be used to make predictions on new data. Steps. Initialize the voting classifier object with the desired estimators and voting strategy. Fit the voting classifier object to the training data. This will train each individual estimator on the data. Make predictions on new data using the fitted voting classifier object. Metrics. Accuracy: the proportion of correctly classified instances. Precision: the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall: the proportion of correctly predicted positive instances out of all actual positive instances. F1 score: the harmonic mean of precision and recall. Visualization plots. Confusion matrix: a matrix that shows the number of instances correctly and incorrectly classified by the ensemble. ROC curve: a plot that shows the trade-off between the true positive rate and the false positive Rate for different classification thresholds. Fine-tune parameters. Weights: a list of weights for each estimator, allowing you to specify how much influence each estimator should have in the final prediction. Flattening: a Boolean value that determines whether to flatten the input array before applying pay. Estimators. Uncertainty methods. Confidence score: the predicted probability of the most likely class for each instance. Ensemble variance: the variance of the predictions of the individual estimators for each instance. Challenges and fixes. Challenge 1: overfitting. If the individual estimators are highly complex, the ensemble may overfit the training data. Sample use case that resulted in challenge 1: using a high-degree polynomial regression model as an estimator in an ensemble for a complex dataset. Fixes to challenge 1: regularization: adding regularization terms to the individual estimators to prevent overfitting. Early stopping: stopping the training process early to prevent overfitting. Challenge 2: poor performance: if the individual estimators are not good at predicting the target variable, the ensemble will also perform poorly. Sample use case that resulted in challenge 2: using a linear regression model as an estimator in an ensemble for a dataset with nonlinear relationships. Fixes to challenge 2: feature engineering: creating new features that are more relevant to the target variable. Ensemble selection: selecting a different set of estimators that are more suitable for the problem. Challenge 3: computationally expensive training: a voting classifier can be computationally expensive, especially if the individual estimators are complex or if there are many estimators in the ensemble. Sample use case that resulted in challenge 3: using a large ensemble of deep neural networks for a complex problem. Fixes to challenge 3: parallelization: using parallel processing to speed up training. Reducing the number of estimators: selecting a smaller set of estimators that are more effective. sklearn ensemble voting regressor. Description: the voting regressor in scikit-learn is a powerful ensemble learning method for combining multiple regression models to improve prediction accuracy. It leverages the strengths of different models by averaging their individual predictions, effectively mitigating the weaknesses of any single model. This process typically results in a more robust and accurate prediction compared to using any single model alone. Inputs. Estimators: this is a list of trained regression models that the voting regressor will combine. Each model should be an instance of a regression estimator like linear regression, random forest regressor, or gradient boosting regressor. Weights optional: this parameter allows you to specify weights for each individual estimator. By default, all estimators are weighted equally. However, if you have prior knowledge about the relative performance of your models, you can use weights to favor certain estimators over others. Outputs. Predictions: the voting regressor outputs predictions for new data points. These predictions are based on a combination of predictions from the individual models in the ensemble. Steps. Training: the voting regressor does not perform any independent training. It simply takes already trained regression models as input. Prediction: when predicting, the voting regressor feeds the input data to each individual estimator in the ensemble. It then combines the predictions from each estimator according to the specified weighing scheme. Metrics. R-squared: this metric measures how well the model explains the variance in the target variable. A higher R-squared value indicates a better fit. Mean squared error (MSE): this metric quantifies the average squared difference between the predicted and actual values. A lower MSE indicates better accuracy. Root mean squared error RMSE. This is the square root of MSE and provides a measure of the average difference between the predicted and actual values. Lower RMSE values are preferred. Visualization plots. Residual plots. Residual plots visualize the difference between predicted and actual values. This can help identify patterns in the errors and assess the model's assumptions. Feature importance plots for some models, e.g., random forests. Feature importance plots can be generated to understand the relative contribution of different features to the prediction. Learning curves. Learning curves can be plotted to assess how the model's performance changes with the amount of training data. Fine-tune parameters. Estimators experiment with different regression models, e.g., linear models, decision trees, ensemble methods to find the best combination for your specific problem. Weights. Adjust the weights assigned to each estimator to fine-tune the ensemble's performance. You can use grid search or other hyperparameter optimization techniques to find the optimal weights. Uncertainty methods. Confidence intervals. While not directly implemented within voting regressor, you can obtain confidence intervals for the combined prediction by analyzing the individual confidence intervals of the estimators. Challenges and fixes. Challenge 1. Overfitting. If the individual models are overfitted to the training data, the voting regressor can inherit this overfitting behavior. Sample use case that resulted in challenge 1. A voting regressor is used with multiple decision tree models trained on a small dataset. The individual trees overfit to the training data, resulting in poor generalization performance on unseen data. Fixes to challenge 1. Use regularization techniques, e.g., L1 or L2 regularization on the individual models to prevent overfitting. Utilize ensemble methods with built-in overfitting mitigation, such as random forests or gradient boosting. Consider using a validation set during training to monitor model performance and detect overfitting. Challenge 2. Bias in ensemble. If the individual models have significant biases, the voting regressor may not be able to correct for them, leading to biased predictions. Sample use case that resulted in challenge 2. A voting regressor is used with multiple linear models, each exhibiting a different bias in the data. The ensemble inherits these biases, resulting in systematically inaccurate predictions. Fixes to challenge 2. Select individual models with different biases to balance out their combined effect. Use techniques like data preprocessing to correct for known biases in the data before training the models. Explore alternative ensemble methods that are less prone to bias, such as stacked ensembles or bagging. Sklearn Ensemble Hist Gradient Boosting Regressor. Description. Hist Gradient Boosting Regressor is a powerful gradient boosting algorithm designed for regression tasks. It leverages the strengths of histogram-based gradient boosting, enabling it to handle large datasets efficiently while maintaining accuracy. Unlike traditional gradient boosting methods that use individual data points, this algorithm uses histograms to group similar data points, thereby speeding up the training process and reducing memory usage. Inputs. XA2D array representing the input features of the dataset. Each row corresponds to a sample, and each column represents a feature. YA1D array representing the target values corresponding to the input features. Outputs. Predictions. A1D array containing the predicted values for new input data. Steps. Initialization. The algorithm starts by initializing a constant model that predicts the mean of the target values. Iterative boosting. It then iteratively builds an ensemble of decision trees by computing gradients, calculating the residuals differences between actual and predicted values for the current model. Building trees, training a decision tree on the residuals to capture the remaining patterns. Updating model, adding the new tree to the ensemble. Weighted by its importance. Metrics. Mean squared error. MSE measures the average squared difference between predicted and actual values. Root mean squared error. RMSE, the square root of the MSE. Providing a more interpretable measure of error in the same units as the target variable. R squared. R2 represents the proportion of variance in the target variable explained by the model, ranging from 0 to 1, with higher values indicating better fit. Visualization plots. Feature importance plot visualizes the importance of each feature in the model, indicating which features contribute most to the prediction. Partial dependence plots show the relationship between a specific feature and the target variable, holding other features constant. Tree visualization allows for viewing the structure of the individual decision trees in the ensemble, providing insights into the model's decision-making process. Fine-tune parameters. Learning rate controls the step size at each iteration. Smaller values result in slower but potentially more stable learning. Maxiter sets the maximum number of boosting iterations. Max depth specifies the maximum depth of the individual decision trees in the ensemble. Limiting model complexity. L2 regularization applies L2 regularization to prevent overfitting. Min samples leave minimum number of samples required to split an internal node. Limiting tree growth and preventing overfitting. Uncertainty methods. Confidence intervals can be calculated based on the ensemble's predictions to provide an estimate of the model's uncertainty in its predictions. Prediction intervals can be used to provide a range within which the true target value is likely to fall. Challenges and fixes. Challenge 1. Overfitting. When the model learns the training data too well and performs poorly on unseen data. Sample use case that resulted in challenge 1: using a high number of boosting iterations maxiter, or allowing trees to grow too deep. Max depth can lead to overfitting. Fixes to challenge 1. Reduce maxiter. Limit the number of boosting iterations to prevent the model from becoming too complex. Decrease max depth. Limit the depth of individual decision trees to prevent them from becoming overly specific to the training data. Increase L2 regularization. Applying L2 regularization can help prevent overfitting by penalizing large coefficients. Challenge 2. Computational cost. Training a hist gradient boosting regressor can be computationally expensive for very large datasets, especially with a high number of features or boosting iterations. Sample use case that resulted in challenge 2: training the model on a dataset with millions of samples and hundreds of features could lead to significant training time. Fixes to challenge 2. Reduce maxiter. Limiting the number of boosting iterations can significantly decrease training time. Consider early stopping. Monitor the model's performance on a validation set during training and stop training when performance no longer improves to avoid unnecessary iterations. Utilize feature selection techniques. Identifying and removing irrelevant features can reduce the model's complexity and improve training speed. Optimize hyperparameters. Fine-tuning parameters like learning rate and max depth can impact training time and performance. sklearn, Ensemble, Hist gradient boosting classifier. Description. Hist gradient boosting classifier is a gradient boosting algorithm that utilizes histogram-based binning for efficient and scalable training. It excels at handling high-dimensional datasets and is known for its accuracy and robustness. Inputs. X a 2D array representing the features of the training data. Each row corresponds to a data point, and each column represents a feature. Y a 1D array representing the target labels for the training data. Outputs. Self-trained hist gradient boosting classifier object. Predict probx returns the probability of each class for each data point in X. Steps. Initialization. The algorithm starts with an initial prediction model, e.g., a constant value. Iterative boosting. The algorithm iteratively builds an ensemble of decision trees by calculating the residuals errors between the current model's predictions and the actual target values. Training a decision tree on the residuals. Updating the model by adding a weighted contribution of the new tree's predictions to the existing predictions. Regularization to prevent overfitting. The algorithm incorporates regularization techniques like L1 and L2 penalties. Metrics. Accuracy measures the proportion of correctly classified data points. Precision measures the proportion of true positive predictions out of all positive predictions. Recall measures the proportion of true positive predictions out of all actual positive data points. F1 score, a harmonic mean of precision and recall. AUC area under the ROC curve represents the model's ability to distinguish between positive and negative classes. Visualization plots. Feature importance plot depicts the relative importance of each feature in the model's decision-making process. Decision tree visualization visualizes individual decision trees within the ensemble, revealing the structure and decision rules. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, illustrating the model's performance. Fine-tune parameters. Learning rate controls the step size at which the model learns from new trees. A smaller learning rate generally results in more stable training but may take longer to converge. Maxiter specifies the maximum number of boosting iterations, i.e., trees added to the ensemble. Max depth sets the maximum depth of each individual decision tree. Deeper trees can capture more complex relationships but may be prone to overfitting. Minsample's leaf defines the minimum number of data points required in a leaf node of a tree. This helps prevent overfitting by ensuring that each node has a reasonable amount of data. Uncertainty methods. Confidence interval provides an estimate of the range of possible values for the predicted probabilities, capturing the uncertainty in the model's predictions. Predictive entropy quantifies the uncertainty in the model's predictions by measuring the expected information gained from observing the true label. Challenges and fixes. Challenge 1. Overfitting. The model may perform well on the training data but generalize poorly to unseen data. Sample use case that resulted in challenge 1 when using a high learning rate and large max depth. The model might memorize the training data and fail to capture general patterns. Fixes to challenge 1. Reduce the learning rate. Decrease the maximum depth of trees' max depth. Increase the minimum samples per leaf. Minsample's leaf. Use early stopping based on a validation set. Challenge 2. Long training time for large datasets. Training can be computationally intensive. Sample use case that resulted in challenge 2. Large datasets with many features or a high number of boosting iterations may lead to longer training times. Fixes to challenge 2. Reduce the number of boosting iterations. Maxiter. Consider using a smaller subset of features. Feature selection. Utilize hardware acceleration e.g. GPUs. Explore alternative algorithms if speed is a primary concern.